So today I want to address issues with AI in the open world, but I thought first I would talk to you a bit about Microsoft Research AI. So the founders of the field of AI in the 1950s laid out 4 pillars of the field of AI, where things are going to be going in the future here. And over the last 60 years, these pillars have been central themes of what we do: perception, learning, reasoning, and natural language. And over the decades, as the field has matured, numerous subdisciplines have evolved into separate and distinct areas of study. And whole new communities have come to the fore and stood up around these technologies. There's been quite a bit of sharing of technical innovations among these communities, but this opportunity to do a lot more and bring these folks together over some key, critical, and persistent challenges. Now, Microsoft Research, in its diversity and breadth, has attracted top talent in each of these areas. And we've thought, wouldn't it be better to think through right now a new organization, a new culture, arrayed around some key aspirations? Just a few, and I'll mention 3 right now: attaining more general intelligence, mastering human-AI collaboration, and studying insights and leading with insights on people, AI, and society. Let me tell you a little bit more about a couple of these aspirations, but just very briefly to touch on where we're going with this, on more general intelligence. We hear the phrase artificial general intelligence all the time these days. It's not clear what that means. It's probably not just one thing, but certainly we can push in a variety of ways to get past our expertise right now in building wedges of competency. In some of our work, we've combined natural language, speech recognition, decision-making and planning and learning into systems like the assistant by my door that could do many things at once. And we've struggled with the idea of how do you better coordinate these competencies. But there's more opportunity and directions to do other kinds of work, to come up with new architectures that combine some technologies, to think through fabrics, potentially using some advances in machine learning, to really address head-on the principles of more general AI. It's the reason why many of us are here, to address some of the mysteries that we see in human intellect. On mastering human-AI collaboration, there's so much upside to basically getting this right, to coming up with principles and thinking through possibilities. How do we augment and extend human capabilities? I often think about all the work in cognitive psychology that's shown us, really with well-characterized studies, where some blind spots, biases, and gaps are in our abilities. Can't we leverage this work and directly and explicitly build computational systems that can extend our abilities in different settings? Now, over the years, in fact, in the late 90s and early 2000s, we did quite a bit of work on leveraging these principles to better remind people to understand memory landmarks, to do attention management, cost of interruption, understand biases and judgment. We want to leverage that work. And in thinking through human cognition and machine intelligence, it's not just about cognitive psychology. There's a lot more to be learned and to learn from actual data sets. And there's quite a bit of design work here, too. How do we design for a mix of initiatives to really get it right? We think there's so much upside into empowering people and amplifying human ingenuity. And on people, AI, and society, there are so many interesting issues rising with the applications coming into the world now in trustworthiness and safety, fairness and accuracy, transparency and explanation, and even more subtle but deep explorations of the human-AI relationship. But with that, let me just get into the topic of my talk now. I wanted to just fill you in on our announcement last week on MSR-AI, given the themes today. I want to talk about AI in the open world now. I'm thinking through, it's more important than ever as we think through the fruits of our labors as researchers. What happens when we take our solutions that we generate in the laboratory and apply them in the open world, whether it be in healthcare or with our agents like Cortana, to understand better how to target our goals and understand what happens in the real world. And of course, you can study different aspects of this gap or chasm, the competency of the systems we develop in the lab in the real world, issues with interaction, ethical, legal, social, and societal influences. But today I wanted to focus a little bit on competency. I think it's an important area, and I'll get back into the other areas at the end. So from the early days of AI, especially in the logic-based AI realm, we had the frame problem, which was a beautiful expression of how incomplete our systems are, including the qualification problem. When I take any action as an agent, do I really know all the preconditions are being met and what they might be? And the ramification problem, what were all the possible effects of action right now? In fact, if you think about people worrying about AI and concerned with AI, it's all about the ramification problem. What are all the effects and influences of these systems in the world? Today, I like to think about, in this probabilistic AI world, this idea of getting the framing right. What's the framing of the problem, the definitions, the distinctions, the key actions and preferences and goals, and the overall intention of the problem solving? The data, is there sufficient data for learning or engineering, sufficient experiences? And then thinking about the fidelity of the system, both the representational and inferential fidelity. Even with infinite amounts of data, do I have the fidelity I need to be competent in the world? I want to first talk about learning about competency as a critical area, citing some wisdom of the ages. Lao Tzu, 500 to 600 BC, somewhere in there, made a very important observation about knowledge and wisdom, saying in the Tao, knowing that you do not know is the best. And probably even more important, and you'll be hearing about technologies in a few minutes, he also asserted, not knowing that you do not know is an illness. The power of learning about competency and learning reliability models for myself goes way back to the late 1990s when I was working with Kentaro Tayama, when he was a vision researcher. We were struggling to find a good face tracker. We had 3 or 4 different versions of face tracking, all very, very different. And they all failed dramatically in different ways at different times that we were having trouble figuring out. So we built models, and we decided, let's build, with machine learning, with data sets, build a model that will actually understand the competency at any moment based on what we call reliability indicators for each separate methodology. And we wove these together where every single algorithm was reporting both the reliability and the signal and the inference. And it turned out when we did this, we were actually magically surprised that the system, this portfolio of methods, each reporting reliability, did very well in unmodeled situations. Facing away, a jolted camera, distraction, lights out completely. It was working beautifully. So we thought, wow, there's something to be said about building more robust systems in the world by developing portfolios and reasoning deeply, having each component of a portfolio reflect about reliability. Now today, methods for learning about competence is very important in the world. We've done deep learning at Microsoft Corporation now and research about deep learning itself, for example, to understand the confidence with which captions are being generated for photos in our PowerPoint offerings, and in the recent Seeing AI work that once in a while will say, I'm not sure, but I think that might be a fence next to a farm. So reliable predictions of performance, or known unknowns, sort of the unknown systems know about, is very critical for even high-stakes applications. So I couldn't resist buying a Tesla several years ago when I heard that pretty soon it would be self-driving. I said, well, how could I not? This is my field. And I was happy in the first few minutes of checking out the new autopilot, which was downloaded about 1.5 years ago. I had it, and I had to go outside and try it out. I said, wow, it's great. Oops. Oh, the system knows when it's not confident enough to continue. And then I basically went back and I grabbed my whole family and I said, check this out. And I went down Lake Washington Boulevard. And it was looking very reliable until the car turned into oncoming traffic without any sign or any signaling at all. I said, okay, well, you know, my wife told me to never put this thing in autopilot ever again. Make me promise. So think about the challenge that the designers of automated cars have, is to think of all the edge conditions, things that you might come over time in the real world. For me, it was another late night encounter with barrels closing off a lane gracefully. Led me to grab the wheel and take over. It wasn't something that was programmed into the car, and I wouldn't have known that ahead of time. And just in March, my car was full of a bunch of execs heading to the exec retreat at Microsoft, and here's what we encountered through my windshield. My guess is that the Tesla designers in Fremont weren't thinking about the rear ends of deer. So I took the thing out of autopilot. So we have the challenge of unknown unknowns, and it's really an important technical challenge, as well as a policy challenge for AI to think through. Well, how do we grapple with unknown unknowns? Well, there are several ideas, right? We can have expanded real-world testing, clinical trials for new technologies. So you don't field the Tesla autopilot all at once. There are some volunteers and some ways to indicate where those cars are on the road. Maybe we do more work with algorithmic portfolios, fail-safe designs that can sort of pick up the slack if something really fails in the end, and thinking about using people as oracles and machines in a variety of ways. Now, one piece of work that captures a direction for a certain kind of unknown unknown, blind spots and classifiers based in training biases, was pursued by Himabindu Lakkaraju, Ajay Kumar, and Rich Kawana, and myself last year. And we published a paper in AAAI this year. And the basic idea is that we often think about training data as being representative, and therefore we can build a good model. But there could be biases, systematic problems with observations that leads to conceptual incompleteness, and of course to model problems and high confidence labels coming out that are just wrong. For example, in trying to distinguish cats and dogs, one of the examples in our papers, you can imagine that you might be missing a whole category like white dogs in your training set and leading to some misclassifications at high confidence. And in some really fabulously interesting work per the direction that it points in, we asked the question, how might we employ oracles, human beings, and use algorithms to triage attention at the blind spots to basically more optimally identify categories of bias and blind spot. And the methodology it basically takes a set of attributes and lays out with set cover a set of concepts that are clustered and lets the system reason about optimizing the probes by human oracles under bounded resources. Just a direction there. Now, another comment I want to make is, yes, we're in a very data-rich world right now, and it's a celebrated data-rich world, but we still often face challenges with data scarcity. For example, we may have data from one setting, but wish to personalize it to a particular person or home, or build a custom tailored system for an application that is not exactly the same as the one for which we have a lot of data. Data scarcity is actually a common problem with opportunities for AI in the open world. And several possibilities include, we're listening here, transfer learning, learning from rich simulations, and learning generative models. Let me just touch on each one of those right now with some examples. Several years ago, I was working with Jenna Weens. Jenna Weens is a professor at UMich now. But when she was my intern, we were very interested in this problem of predicting the risk of infection from large-scale electronic health records. Which patients were at the highest risk for coming down with a nasty intestinal infection called C. difficile. And we employed a lot of data from a large urban hospital in Washington, D.C., here listed as Hospital C. But then, and we built a nice model, and then we heard interest from other hospitals in the same family of hospitals, not that far away, in Maryland and other places. Can we use that model in our hospital? Well, it turned out the original model didn't work all that well when you try to translate it, because the different patients, prevalencies, different covariate influences among observations and causes, and even observational definitions would change. In fact, you see the overlap there in this little Venn diagram. The symptoms even used in the electronic health records are different from hospital to hospital. But it turns out we didn't have enough data in Hospital A to do a good job. What can we do? We dove into the literature on transfer learning and found a multitask method that really could be used to warp and bend the rich data assets in Hospital C to enhance Hospital A. Now, my sense was a lot of work, we need to do a lot more work on this. We got things to work by hook or by crook, but there's a lot of learning to do in the transfer learning area. In another approach, which has implications for rich learning on small devices from very small numbers of samples. It's also exciting in some ways for a model of cognition, I think. It's intriguing to me, is work on taking a knife. I had to ask our PR people, our HR people if that was okay to show a knife up here, clipping off the top layer of ImageNet, which was trained on a million photos. What you end up here now is a system that can generate in this cutoff layer a vector of real-world oriented features. It's learned how to see stuff across 1,000 categories. Could that be used as a generic foundation for doing lightweight learning, decision-making from small numbers of samples? And the idea basically is we compress this further. We have some nice compression algorithms we're working on. Want to put this whole thing on a Raspberry Pi, have very fast-paced training so we can take a few pictures, let's say 2 or 3 pictures of different people in a team, and have the system recognize things right away. So the approach was at the top layer, we're going to take that vector, and instead of doing something heavy-duty, we're going to use, for example, k-nearest neighbor and cluster for our learning approach to recognize. The whole thing fits in the palm of a hand. I'm sure this can be miniaturized. This is Rich Caruana's device, lead of the effort here. But let me show you a little bit about a little video here. This is Rich, more energetic than usual because he's been sped up. Taking 4 photos of Shamsi Iqbal. Many of you know, does work in attention with us. And we'll see he did this also with Shane Williams, Ofer Deckel, Grija Ranaday. And now he's going to try out the system and see how well this works. And we see that it's really leveraging the rich features with little amounts of data. People putting hats on, taking the hats off. But imagine someday you get a little device that's a part of your thermostat or your doorbell, and you train it up, and it's using the power of ImageNet compressed onto that model, but doing lightweight learning at the top level, all by way of that knife procedure, that surgical action. Another approach to dealing with scarcity of data is to use simulators, rich simulations. Many of the successes in games of perfect information or other gaming scenarios are based on relatively simple structured rules of a game. Even for the games that are not a perfect information, these systems can actually play trillions of games with one another. I say with itself too, and can actually learn from that kind of intensity of engagement, which is very difficult to do with realistic worlds. That's why we're often strapped. We don't have the same kind of power and successes with open world, realistic, human-oriented settings. What might we do to learn to optimize action plans in simulated environments? Well, as many of you know, back in February, Chital Shah, Ashish Kapoor, Diva Bipta Day, and Chris Lovett got together with others and built a rich simulator that has incredible fidelity, everything from and physics, wind patterns, weather, and we can actually fly actual live drone code to power up drones in these worlds. And the drones think they're actually really flying in the world, but especially the drone controller. But even the sensors and the perception is done well. So we see what the actual, in a realistic setting, what a drone sensor would actually be seeing. Now, the idea basically is if we could do this, might we be able to learn in these worlds? And I'm happy to announce that we just extended AirSim to talk directly through APIs to deep learning algorithms right now. We can collect data and learn from them, your deep learning platform of choice. And the idea basically, just to give you a sense for what we're working on right now, the idea basically is, can we actually, for example, fly our system around, build a CNN that does lightweight depth analysis very quickly, compress it, understand the trades between different versions of our ability to do coarse vision, build maps and do reinforcement learning, and do this trillions of times to build a smart device out in the world that might be close to what we want it to be before it even touches the real atmosphere, flying in the in the atmospheres inside AirSim. That's active work right now. Another area is learning generative models. There's been some magic in our community recently over the last 3 years, starting with, I'd say, the generative adversarial network efforts and other approaches to learning expressive probabilistic generative models from small numbers of samples. I've been very impressed by that. In that same spirit, some recent work by Sebastian Noazin and team in our Cambridge lab was looking at just taking a few training examples. For example, a folder of pictures of the same person from different views and different lighting conditions, or very similar looking people with different, in the same kind of lighting or shading or color. And so you see, you get a sense here for the prospect of building a latent space and having smooth control over a latent space just from a few samples. I believe these methods, including related methods right now, on inferring generative models will be very powerful moving forward in how we actually learn in semi-supervised ways. I wouldn't say unsupervised, because there is a signal here coming, but it's very lightweight. I was also impressed by work on not just relying on learning, but injecting what we know about the world, the physics of the world, the way lighting works in the world. So work by Pushmeet Kohli, Josh Tannenbaum, Tejas Kulkarni, and others looked at the idea of putting a physics engine, a graphics simulator in the deep learning pipeline itself, and that is part of a generative model. Now, here's the intuition. Once you have that kind of thing, you can take faces and understand how to rotate them and shade them with these disentangled representation, right? So you can actually basically understand, the system understands, well, you know, if I had different illumination, what would that face look like? If this human being nodded, what would that look like? So I could better recognize that, so I have a richer sense for a generative model of data, or a shake, for example. Very, very exciting work in the idea of getting some of our physics and causality into our generative models directly to speed things up and not rely just on associations and learning. So with what I said about moving into the open world with our technologies, I was talking mostly about competency right now, data scarcity, data morphing, how to make these systems more effective in the world and understand them. But coming into a world where AI technologies are being applied in high-stakes settings like healthcare and criminal justice brings to mind the responsibility and the care we need to scrutinize these systems when they're out in the world. There's a bunch of work to be done, technical, legal, ethics, in the ethics realm, and other areas. And there are growing responsibilities for us as research scientists, us as Microsoft Corporation and other companies, and the wider community to develop methods and tools and processes that address potential concerns. A couple of years ago now, there was some interesting work investigating with Julia Angwin and others, investigating biases rising deep in data sets for criminal justice, systems that were being used to advise judges across the country on decisions about bail and imprisonment. And as an article on this work showed in the ProPublica venue, you have folks that are being indicated as high risk versus low risk. And when you dug into the data, it seemed that there were some systematic biases that could be explained as observational bias and other forms of blind spot, unknown unknowns. Now, this is a very high stakes, almost scary situation, but even in lighter stakes settings, like Microsoft's cognitive services, we want to think through the details of possible biases and understand methodologies and best practices. So this shows you a demonstration of Microsoft's cognitive services that does emotion detection that could be woven into applications with simple calls. among just like other applications, other cognitive services. And last year, Ayanna Howard visited us, and we decided to dive into looking at some of the cognitive services. And we found that Microsoft's cognitive service for emotion was failing in certain ways on children, young people. Looked at the training set, and it turned out the distribution of training data was, as you might expect, centered around adults. But we characterized the challenges and the problems, and we even showed how we can generate a contact lens, almost like for the Hubble telescope, you'd put over the system for children if they're being examined by this emotion detector. But it suggested that it's possible to think about best practices for all of our cognitive services and to share them with the more global community, as well as policies and procedures, not just about biases, but about the unknown unknowns, safety critical issues, human-AI collaboration, and issues that might arise there, and deeper issues with our relationship with AI systems as people. And so several months ago, we stood up the Aether Advisory Panel at Microsoft. This is Aether is an acronym for AI and Ethics in Engineering and Research. And we put together this panel as key leads of each division at Microsoft, of passionate leaders in those divisions, working through issues coming up, for example, in Windows and in our cloud services, and in our research area, and beyond. And this panel reports directly to Satya Nadella and to our senior leadership team. On broader outreach, we've been very passionate about working with colleagues across industry, starting with links to Amazon, Facebook, IBM, Google and DeepMind, and Apple and other teams. And now this partnership on AI, as we call it, has grown to include nonprofit organizations and is a nonprofit with a balanced board of directors that balances corporate and nonprofit NGO leadership. People can get involved with the Partnership on AI by going to partnershiponai.org. The group is looking for broad participation over the next few years as we stand up a very important set of efforts around best practices in AI at the intersection of AI, people, and society. So, for my title, we need to really address key scientific foundations about AI in the open world. In some ways, I see AI in the open world as framing a science of incompleteness in our reasoning systems and how we grapple with the incompleteness in systematic ways, and coupling the technology with policy. And it's not just about the core science. There are engineering practices that are framed and motivated by this work. And a lot more discussion we need to do about AI, people, and society. And we'll be having a panel on the breadth of issues tomorrow in these realms. So there's much to do. I'm extremely excited about possibilities. In some ways, I was just telling some folks backstage that I gave a talk at my AAAI presidential lecture called Open World AI in 2009. And I view these comments now and these ideas as kind of an update 8 years later. And it's interesting to see. I would have been really excited to see this video way back when, to see where things have headed, especially in the influence and impact these technologies are having on the real world. It's an exciting time, and I think we have a lot of work to do as technical leads in this community. Thanks very much.